In 1932, California faced a problem that was killing livestock and making life miserable for millions. Mosquitoes were not just a seasonal inconvenience. They were disease vectors, carriers of suffering, and in those years before modern synthetic insecticides, there was no effective way to stop them. The malaria that mosquitoes transmitted was common across the American South and Southwest. Dengue fever showed up in coastal cities every summer, causing fever, body aches, and sometimes death. Yellow fever still haunted population memory even though it had not killed anyone in most American cities since the 1800s. Mosquitoes meant disease, and disease meant real death and disability on a scale that is hard to imagine in our modern time. When scientists and public health officials looked at the mosquito problem, they saw two possible solutions. The first solution was infrastructure. This meant draining swamps and marshes, filling wetlands, building aqueducts and ditches to move water where people did not want it to stagnate. This solution required engineering expertise, skilled labor, ongoing maintenance, and significant capital investment. It took years to plan and implement. It was expensive. The second solution was biological control. Someone had noticed a small fish from Texas and Louisiana that ate mosquito larvae by the thousands. The fish was called Gambusia affinis. It seemed like an answer sent by nature itself. It was small, hardy, and it reproduced quickly. Best of all, using it required almost no money. You could catch some fish in a bucket, dump them into a pond or marsh, and let nature do the work for free. Or so they thought. The California Department of Fish and Game looked at this little fish and saw opportunity. They saw a way to protect public health without expensive infrastructure. They saw a solution that could be deployed everywhere, anywhere there was standing water. They made a decision in 1932 to introduce Gambusia affinis into California water bodies. Before anyone could stop them, that decision would transform ecosystems across an entire continent and cost billions of dollars in management and lost biodiversity over the century that followed. Before we go any further, I need to pause for a second. If you are watching this because you are thinking about how to live better on less money, understanding what happened with the mosquitofish is absolutely crucial. This is a story about decisions that cost nothing up front, but everything over time. This is about how governments decided to move a species around the world to avoid spending money on real solutions. This is about choosing convenience over consequence. This is about your tax dollars funding ecological invasions that nobody can reverse. This is about the hidden costs that appear in budgets decades after the initial decision, compounded year after year until they exceed the cost of doing it right the first time. If you are here for that story, the story of how cheap decisions become expensive ones, make sure you are subscribed. You do not want to miss what comes next. The mosquitofish came from the coastal bayous and marshes of Texas and Louisiana. These are warm water systems where rainfall is abundant and swamps merge with rivers and brackish estuaries. The fish evolved in that specific ecosystem. It is a live bearer, meaning it does not lay eggs that require weeks to hatch into fry. Instead, females give birth to fully formed young, sometimes more than 100 at a single birth. These babies are independent from the moment of birth. They do not require parental care. They mature in 6 to 8 weeks. They tolerate fresh water and brackish water. They tolerate water that is too warm or too cold for many other fish. They tolerate water with low oxygen levels. They eat mosquito larvae obsessively. A single female can populate a pond in a season. A single introduction of 10 fish can become 10,000 fish in a year. For public health officials in the 1930s, with the memory of epidemic disease still fresh and the burden of malaria and dengue fever on the population still heavy, the mosquitofish seemed like a miracle. Here was a solution that required no infrastructure spending, no engineering, no labor costs, no ongoing maintenance. The fish would control the mosquitoes all by themselves. All you had to do was catch them and move them. By 1934, California had introduced mosquitofish into more than 400 water bodies. By 1950, they had spread to 42 states. By 1970, they had reached nearly every state in the Union, plus Hawaii and Puerto Rico. They had been exported to Australia, South Africa, Europe, and Asia. No one was keeping track. No one was asking what the fish would do to native species. The assumption was that they would eat mosquito larvae and die or exist in equilibrium with native species. No one thought they would spread so wildly, outcompete native fish, or destroy ecosystems. But that is exactly what happened. The mosquitofish are aggressive predators. They will eat the eggs of other fish. They will attack tadpoles and small aquatic vertebrates. They will outcompete native fish for food resources. They are not picky eaters. Give them mosquito larvae, and they will eat them preferentially because mosquito larvae are easy prey. But give them anything else, small fish, crustaceans, insects, amphibian eggs, worms, and they will eat those too. The problem is that mosquito larvae are seasonal. They show up in spring and early summer when standing water warms up. But the fish never leave. They stay all year. They overwinter in the mud at the bottom of ponds and springs. When mosquito season ends in late summer and fall, they turn to whatever else is available. And in many water bodies, what is available is rare, endemic species that evolved in mosquito-free environments for millions of years. The first scientist to document the ecological damage caused by mosquitofish introduction was Jack Rutter, a research biologist studying a series of ponds in the Sierra Nevada foothills in California in 1950. Rutter noticed something very odd and troubling. Native fish that had been common before mosquitofish introduction were now rare or completely gone. The native fish species of the Sierra Nevada foothills had evolved in isolation. Some of them lived nowhere else on Earth. They had never encountered aggressive predatory fish like mosquitofish. They had no evolutionary defense against them. Rutter published his findings in a local scientific journal. Very few people read it. The California Department of Fish and Game acknowledged his findings, but did nothing. By that time, the mosquitofish were already in thousands of water bodies. You cannot unintroduce a species that has become so widespread across so much territory. The decision had locked in its consequences forever. By the 1980s, a full 50 years after the first introductions, ecologists were beginning to understand the full scope of what had happened. The mosquitofish had not just reduced mosquito populations in the places where they were introduced, they had altered entire freshwater ecosystems. In California's Central Valley, endemic fish species that had survived in small populations for millennia were now extinct. The Tule perch, named for the Tule bulrush that grows in Central Valley wetlands, the valley springfish, a species found only in the warm springs of the Central Valley, the thick-tailed chub, another Central Valley endemic, the Shoshone pupfish, a tiny fish from alkali springs in the Great Basin. All of these were gone or critically endangered. Not just because of habitat loss, though that was part of it, but because a predatory fish from Texas was eating them. The mosquitofish affect the low-cost living equation in ways that most people never think about when they are sitting at home or at work, going about their daily lives. The fish were introduced because infrastructure costs money, real money, the kind of money that shows up in budgets and requires votes and funding decisions. Draining wetlands, dikes, and levees, building water control systems, developing synthetic insecticides, these were all expensive in the 1930s and 40s. They required significant planning, technical expertise, engineering, labor, and materials. They required paying for things up front. They required ongoing maintenance and skilled workers. The decision to use the mosquitofish instead was a choice to transfer cost from the present into the future. It was a choice to trade a visible cost today for an invisible cost tomorrow. And like all debt, eventually it comes due. Eventually the bill comes to your address. Eventually you have to pay it. And by then the interest has compounded so much that the cost is far greater than paying the original bill on time. The mosquitofish impacts native aquatic life in multiple ways. First, they are direct predators that eat amphibian eggs and larvae, which is catastrophic for frogs, toads, and salamanders that rely on temporary ponds and marshes for breeding. In the western United States, frog and toad populations have been declining for decades. Habitat loss is part of that story. Pollution is part of that story. Disease is part of that story. But the mosquitofish are a major part of that story too. They are present in many of the places where amphibians used to breed. Second, they compete for food with native fish. Most small fish in wetland and pond and spring environments eat the same things. Mosquitofish eat small insects, crustaceans, zooplankton, aquatic worms, snail eggs. When mosquitofish arrive, they monopolize that food supply. They are more aggressive than native fish. They are quicker. They breed faster. Native fish are outcompeted. Native fish starve out. Third, they alter the food webs that support all the aquatic and semi-aquatic wildlife in an area. Dragonflies rely on small fish as predators of their nymphs, which creates a balance in dragonfly populations. Water beetles, aquatic snails, are all affected by the presence of mosquitofish. The entire community of life changes. Fourth, they change the behavior of native species. Many small fish and amphibians will not breed if predatory fish are present. They sense the danger and avoid laying eggs in water where mosquitofish hunt. The presence of the fish alone is enough to prevent reproduction, even if the predation itself is limited. The consequences have been particularly severe for endemic species, fish and amphibians that live nowhere else on Earth. California, the Southwest, and the Great Basin are home to hundreds of endemic species that evolved in isolated springs, marshes, and small streams. These species survived millions of years without any predatory fish. They evolved life histories and behaviors adapted to that predator-free environment. They did not evolve the quick reflexes or the defensive behaviors that fish living with predators develop. When mosquitofish arrived, many of these species went extinct within years. There was no adaptation, no time for evolution to find a new equilibrium. The species simply disappeared. The desert pupfish is the most famous example. These are tiny fish, no more than an inch long. Some species are only half an inch. They are colorful, with spots and stripes and bars along their bodies. They evolved in isolated desert springs in Arizona, Nevada, and California. There are more than 30 species of pupfish found nowhere else in the world. Many of them are found in only a single spring or a single small group of springs. Some species have populations in fewer than 100 individual fish. These fish represent millions of years of evolution in isolation. They are living fossils, survivors from a time when the Southwest climate was different, when these springs were more numerous and more connected. In spring after spring across the desert, mosquitofish were introduced to control mosquitoes. The pupfish, with no evolutionary adaptation to predatory fish, could not survive. Entire species were eradicated. Some survived only in captive breeding programs in universities and zoos. Today, several pupfish species exist in the wild only in springs that are protected from mosquitofish introduction, or in isolated habitats so small that introducing them would be impossible without fencing out the mosquitofish. It is a strange and expensive solution to the problem that mosquitofish were supposed to solve cheaply. Nevada, California, Arizona, and New Mexico have spent millions and millions of dollars over the past 20 years trying to remove mosquitofish from sensitive habitats. They pump poison into springs to kill the fish. They drain ponds and keep them dry for weeks to kill the mosquitofish in the mud. They put fish screens on outlets to prevent mosquitofish from spreading to adjacent water bodies. They maintain these screens forever, year after year. This is the cost that appears in budgets decades after the initial decision to use mosquitofish. This is the hidden expense of choosing cheap and fast over safe and lasting. This is money that would never have been spent if someone had made a different decision in 1932. The cost of management is staggering when you add it up. California alone has spent an estimated $30 million or more over the past 50 years trying to deal with mosquitofish impacts. That does not include the loss of endemic species, which cannot be quantified in money. That does not include the cost of maintaining breeding programs for endangered fish. That does not include the cost of protecting critical habitat with monitoring and maintenance. When you add all of these costs together, the total probably exceeds $100 million just in California, and California is just one state. Other states have similar programs. Multiply that across the country, and the total cost is in the billions of dollars, all to manage a problem that was created by trying to save money. In the eastern United States, the mosquitofish problem manifests differently. The East has more diverse native predatory fish communities. The ecosystem is more resilient. The mosquitofish is not driving species to extinction at the same rate that it is in the West. But the mosquitofish still changes the dynamic. Largemouth bass and bluegill and crappie have co-evolved with frogs and salamanders and native fish for millions of years. There is a balance, there is an equilibrium, but add the aggressive mosquitofish into the mix, and that balance shifts. The mosquitofish is not a native species adapted to the local ecosystem through millions of years of evolution. It is an invader that plays by different rules. It is a faster breeder, a more aggressive competitor, and more willing to eat eggs and larvae than most native fish. The result is subtle but consistent. Native species decline even in places where mosquitofish are not the primary predator. The mosquitofish are now found in every state except Alaska and Wyoming. In almost all states, they are self-sustaining. They breed wherever introduced. They spread through connected water systems like rivers and canals. They persist even in harsh conditions that would kill most fish. A mosquitofish can survive in ponds that freeze solid in winter by burrowing into the mud and entering a state of torpor, a kind of hibernation where their metabolism slows almost down to nothing. They can survive in ponds that turn anoxic in summer by gulping air at the surface. They can breed in water so brackish that other fish cannot tolerate it because it is too salty. They are almost unkillable and almost impossible to keep out of a water body once they arrive. The question of how to deal with the mosquitofish is now a permanent part of the work that fish and wildlife agencies do. In California, the state that introduced the species in the first place, there is an entire division dedicated to finding mosquitofish-free water sources for threatened and endangered fish. Scientists keep lists of springs, streams, and ponds that have never been invaded. They protect these places as if they were the last refuges of some critical human resource, because they are. They are the last places where native fish can breed without the constant predation of mosquitofish. These protected places are worth millions of dollars in terms of land value and management cost. They exist only to keep mosquitofish out. This is the legacy of a decision made more than 90 years ago. Other countries have had their own mosquitofish problems and their own expensive lessons. Australia introduced mosquitofish into wetlands to control mosquitoes, following the American model. The fish invaded native wetlands, marshes, and swamps, and displaced species that had evolved isolated from predatory fish for millions of years. Australia's native fish fauna is particularly vulnerable because the continent has few species of predatory fish in freshwater. Most of the fish in Australian freshwater systems are small and not predatory. When mosquitofish arrived, they had almost no competition. They had almost no natural predators. They decimated populations of endemic fish and amphibians across the continent. Today, Australia spends millions of dollars every year managing mosquitofish populations in protected wetlands. Australia has also spent money on research trying to understand what mosquitofish have done to native Australian fish. South Africa introduced mosquitofish for the same reason. The fish spread into the Cape Floral region, one of the world's most biodiverse regions on a per-square-kilometer basis. The Cape has more endemic plant species than almost anywhere else on Earth. It also has many endemic freshwater fish and amphibians. Mosquitofish introduction damaged freshwater ecosystems across the region. Many endemic fish species declined significantly. Today, South Africa lists mosquitofish as an invasive species and spends significant resources trying to prevent their spread into critical habitats. The country has also spent money on research and on removal programs. In Europe, mosquitofish were introduced into Mediterranean countries to control disease vectors and reduce mosquito populations. The fish spread into rivers and wetlands and competed with native fish. Some of Europe's endemic fish, species that had survived for millions of years, were displaced. The European response has been to designate mosquitofish as a prohibited species in many countries. New introductions are illegal. Imports are prohibited, but the fish that are already established are difficult to remove. They have become established in Spain, Italy, Greece, and other Mediterranean countries. They are still spreading through connected water systems. The story of the mosquitofish is a story about the hidden costs of convenience. It is a story about decisions made for reasons that seemed sound at the time, without asking what the full consequences might be. It is a story about the way cheap solutions often turn expensive in the long run. It is a story about the difference between a cost that you pay today and a cost that you defer and that compounds over time. When governments decided to introduce mosquitofish, they were making a choice. The choice was between two different ways of managing disease risk and mosquito populations. One way was infrastructure. That meant building, maintaining, and paying for systems that would prevent mosquitoes from breeding. Drainage projects, water systems, even the development of synthetic insecticides. These were all expensive in the 1930s and 40s. They required upfront capital investment. They required ongoing maintenance. They required expertise and planning. There was a cost that showed up in the budget today. The other way was to introduce a predatory fish and let nature do the work. That cost nothing, or so it seemed. No budget item, no funding request, no evidence of expense. Just a few fish in a bucket and instant mosquito control. The hidden cost was that the infrastructure way would have been a reversible decision. If a drainage project had unintended consequences, you could restore the wetland. Infrastructure decisions, even bad ones, are usually fixable. But releasing a living creature into the environment is one way. Once the mosquitofish spread, there is no way to undo it. You cannot uninvent a species. You cannot make it go extinct because you changed your mind. You cannot put the fish back in the box they came from. The low-cost living lesson is not that all cheap solutions are bad. It is that cheap solutions that transfer costs into the future are dangerous. They are dangerous because future costs compound. A $100 project today that avoids a future problem is better than a $1,000 management cost tomorrow. But a $10 project today that creates a $1,000 problem 30 years from now is a bad deal. The mosquitofish was the $10 solution that created the billion-dollar problem. The mosquitofish story also illustrates something important about how ecosystems work. Ecosystems are not simple systems where you can change one thing and predict the outcomes with certainty. They are complex networks of interactions. A fish that eats mosquito larvae also eats other things. It competes with other species for resources. It changes the behavior of the species around it. It changes the food webs that support larger animals. A frog that might have laid eggs in a pond will not lay them there if it senses mosquitofish predators. A native fish that might have dominated a pond will be outcompeted if a more aggressive fish arrives. A dragonfly population that was regulated by predation from native fish will explode if a new predator arrives and kills all the native fish. These chains of consequence can extend far from the original action. They can affect species that have no direct contact with the mosquitofish. They can change the entire character of an ecosystem. Today, mosquito control is done with better tools and better strategies. Insecticides have improved significantly. They are more targeted, more effective, and safer than the insecticides available in the 1930s. Mosquito surveillance programs now use traps and sampling to identify breeding sites and allow targeted intervention. Public health agencies use a combination of approaches that is called integrated pest management. This approach uses insecticides where absolutely necessary, habitat modification where possible, and public education to reduce human-mosquito contact. The mosquitofish is rarely introduced anymore, particularly in developed countries where there are better alternatives. But the fish that were introduced in the 1930s, 1940s, and 1950s are still out there. They are still breeding. They are still affecting ecosystems. They are still an active management problem for fish and wildlife agencies. The question of what to do about the mosquitofish is a permanent question that fish and wildlife agencies face every day. There is no realistic option to eradicate them completely. The fish are too widespread, too well adapted to too many different environments, too good at reproducing. The only option that remains is management protection of the habitats that have not been invaded, careful monitoring of populations in areas where they threaten endangered species, and acceptance that some losses are permanent. This is the long-term consequence of a decision made 90 years ago. This is the price of choosing cheap over careful. If you are thinking about how to reduce costs and live better on less money, the Mosquitofish story offers a crucial and powerful lesson about hidden costs and deferred consequences. It is tempting to choose the solution that costs absolutely nothing now. But if that solution creates significant costs later, you have not actually saved money at all. You have just moved the expense into the future and made it worse by compounding it over time through years and decades. This applies to personal decisions as much as it applies to public policy decisions. If you defer maintenance on a house, you do not save money. You just create larger repair bills. If you avoid paying for quality tools or materials, you end up replacing them more often at greater cost. If you avoid preventive health care, you end up with emergency medical costs that are far more expensive. Cheap now almost always means expensive later. The Mosquitofish decision is also a lesson about the importance of asking questions before making changes to the natural world or to any complex system. Before you introduce a species, before you alter a habitat, before you implement a solution to a problem, it is worth asking what else might change. What else eats the thing you are trying to control? What else competes with the solution you are introducing? What happens after 5 years, 10 years, a generation? These questions are not always easy to answer, but they are worth asking. They are worth research and consideration and careful thought. In the case of the mosquitofish, scientists could have asked these questions in the 1930s. They could have studied the fish in its native range and asked what it would do in a new environment. They could have conducted careful experiments before introducing it into hundreds and hundreds of water bodies. They could have been cautious and gradual. Instead, they were fast and confident. They assumed that a fish that ate mosquito larvae was a complete solution to a mosquito problem. They did not account for everything else that would follow. Today, we have better science and better tools. We understand ecosystems better than we did in the 1930s. We have regulations requiring environmental review before introducing species into new places. But the impulse to find quick solutions is still there, as is the willingness to accept a risk that someone else will pay for. Every time a species is introduced into a new habitat, there is potential for the story of the mosquitofish to repeat, and every time it does, the cost is paid by the natural world and by the people who have to manage the consequences decades and centuries later. The mosquitofish are in every state for a reason. They work at eating mosquito larvae and reducing mosquito populations. The problem is they do other things too. They eat native fish and amphibian eggs. They compete with species with no defense against them. The solution to a mosquito problem should not destroy native species that share that habitat. But with mosquitofish, that is exactly what happened. The solution to one problem created multiple other problems that persist. Living well on less money means making decisions that have lasting value and real consequence. It means avoiding cheap solutions that create expensive problems later on down the road. It means thinking carefully about the long-term consequences of your choices and your decisions. The mosquitofish are still spreading, still breeding, still affecting native species in water bodies across the country today. Every year, more money is spent trying to manage them across the country. Every year, more populations of native fish become extinct in protected areas. Every year, the original 1932 decision gets more and more expensive. This is what happens when you choose the cheap solution without asking what the full long-term cost will be. This is why mosquitofish are in every state and still spreading. This is why the hidden costs continue to be paid 90 years later and will continue for generations to come.